seems like it kind of wants you to make you brush your teeth, right? I mean, my goodness, you think they would have started brushing their teeth long before this got this bad. But whether it's, thank you, whether it's Coca-Cola or... What's the acid in there that's doing the damage? Well, there's several acids, but anybody know? There's carbonic acid, dissolved carbon dioxide. There's phosphoric acid. There's probably some benzoic acid. There's a number of acids in there. So you can abuse really anything, but if you know, do what you're supposed to do, these products can really help life instead of hinder it, okay, and make life a little better. So acids and bases are really important. They're all over the place. So let's start with strong acids. And let's see. How do I do this? I have to do control click. Ah, look at that. See, I can't get the control button. Yeah. The other one was kept locking up on me. So I had to do something. But now I can't get my little buttons. Oh, yeah. That's what I got to learn how to do, right? Pull up the keyboard. Well, I already got this. It's not activating it. Where's my little movie? I'll have to go find it. Let's see. Strong acid and weak acids in water. Here it is. Okay. Oh, everything's messed up. Can you see what's going on there? What they did is they bubbled some HCl in water. And you see all the little molecules flying around in there? Right? And the HCl is supposed to look like this. And in water, does it fall apart or do they stay together? In fact, are there any HCl molecules left? All right? No. So you would call this full deprotonation, or it can 100% dissociates from HCl into H+ and chloride anion. Okay. However, if you take a different type of acid, hydrofluoric, or once this one's done, they'll click on the hydrofluoric button. They'll bubble some hydrofluoric gas in there. Now the little green spheres are the fluoride anions. So in water, now they're not showing the water molecules, they're just showing the hydrogen fluoride. One of them broke up. Okay. So there's some differences between compounds in water. So to be a little more specific, we have strong acids, Jerica, and we have weak acids. Strong acids are blank % dissociated in water. Well, according to that video, you can do better than 50. 100%, right? Whoa. 100% dissociated in water. We need to know the names and formulas of the 6 strong acids. And then, I don't know, Victor, I didn't have you last semester, but I had, didn't have James. I had Daisy, right? Daisy, I told you to memorize all those 6 strong acids. Do you remember them still? Oh yeah, hydrogen bromide, HBr, HCl. I use the periodic table, and you have half of them. Not HF. HBr, HCl, I. So the periodic table is going to give you half. All right? All those halogens. HCl, HBr, and HI. Hydrobromic, hydrochloric, and hydroiodic acid. Okay. We have 3 more. Who else did I have? Jonathan? Derixa? No? Jasmine. I don't think I had you last semester, did I? Oh, do you know them? Who knows them? There's 3 left. There's sulfuric. Oh, yeah, no, sulfate, good. Sulfate has a -2 charge, right? So that means I can fit 2 hydrogens on there. He's right, H2SO4. That's sulfuric. 2 more. Nitric. Okay, now nitrate is NO3 minus. So I can put how many hydrogens on it? Just 1. So I'll be HNO3. We can erase these charges. Okay. Nitric. And then we've got 1 more. That's no. Phosphoric isn't one of the 6. We have hydrochloric, HCl. I'll give you here. Let's do this. How do I erase? It's supposed to erase. Perchlorate can take 1 H. So you would call this what acid? Perchloric. Okay. Now, Victor, I'm going to ask you to do the impossible. There are a gazillion, literally, innumerable acids on this planet. And every single one of them, you have to figure out whether it's strong or weak. And you can do that if you know one little trick. Doesn't matter what I give you, right? And usually we recognize acids how? You look at this formula, oh, that's probably an acid. How do they usually write them? A hydrogen out front of the formula, right? Okay, but how do you tell whether it's weak or strong? Yeah, exactly. If it's one of these 6, it's strong. If it's not in the list, like someone mentioned phosphoric, not on the list, so that must be weak. So that's why you have to know the names and formulas of these 6. Then you know the rest of the acids on the planet. Okay? Know the names and formulas of all those 6. So in general, for strong acids, we can write, they'll dissociate 100%. 100%, right? To H plus and A minus. And it's kind of like sig figs. We're going to talk about it once and then never talk about it again. We're going to write it the way we're supposed to write it, then never write it this way again. We're not supposed to write H plus. We're supposed to write what again? How it actually exists in nature. H. What do we call it? Not H plus in water. This didn't protons, bare protons weren't supposed to. H3 hydronium. We're supposed to write H plus this way. So the water grabs onto the bare proton and makes hydronium. We're still left with what? A with a minus. Okay. So, but this is how we'll be writing it all the time. Okay. Otherwise, we have to add water to both sides, and folks just don't like doing that. Yeah, it's understood that this is really that. Okay. Strengths of conjugate acids and bases. So we've got 2 columns. One has a whole bunch of acids. The other one has a whole bunch of bases. And if you look closely, they're conjugates of one another, straight across. Okay. Let's see if we can play around with this table a little bit. Victor, which conjugate acid is the strongest listed up there? Perfect, right? You're reading the table right if you see that. Which conjugate base is the weakest, James? ClO4 minus. Does that make sense? Right? HClO4 goes to perchlorate and hydrogen ion. But it goes 100% because HClO4 is one of those strong acids, right? Well, that means that perchlorate must be extremely weak. He's such a weak base, right? Because he's the conjugate base of the strong acid. He's such a weak base, he can't grab a proton and go back. Extremely weak. So maybe it seems to you, Jasmine, the stronger the conjugate acid, then the weaker the conjugate base. Exactly. Okay. A few more things about this table. Roland, we've got hydrogen sulfide, or hydrogen sulfite. Which one is a stronger acid? H2SO3. Right, you agree? Right, because it's higher in the table than the H2S. H2S is way down there, so definitely H2SO3. Do you see any compounds in the table that can act like an acid or a base, Daisy? Can something act like an acid and a base according to this table? Does anyone see anything on both sides? Victor? HS negative. Is it on? Let's see. Here's HS negative. Oh yeah, there it is. Okay. There's several. Water is on both sides. Okay. So there's several compounds, and that's gonna make things a little more confusing, but it's all right. Predicting acid-base reactions. So we're going to be given the reactants. Not only do we want to predict the products, but we have to predict the direction the equilibrium is going to lie. It's either going to shift. In other words, if you draw an arrow pointing towards the products, that means at equilibrium, you're going to have almost all products. If you draw an arrow pointing towards reactants, that means the reactants are going to dominate, right? There's going to be mostly reactants at equilibrium. Okay. So there's some tricks to doing this. Two, in fact. Acid-base reactions are commonly of the form above, and the reactants are always, Jamie, what would you say? The reactants are always conjugates. Yeah, these guys are conjugates. 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 Okay. All right. Jonathan, then we have to draw an arrow. Either we have to draw this arrow pointing towards the reactants of the products, and this direction of this arrow is always going to point towards the blank acid. The stronger acid? Everybody agree? Not so sure. So we have to point it toward the side where it's going to stay there, right? It's not going to dissociate. It's just going to form, and it's going to stay there. That's a weak acid does that, right? A weak acid does that. So the weaker, the better. Okay, so all we're going to do is look at, we have that nice table. We'll compare this acid with that one. And if the blue one is weaker, point it towards it. That's all we're really going to do. So let's try this first one. Well, we don't know which one, but predict the products. Okay, now Jamie, if we're going to predict the products, it's going to look like what we have up here. So we have to recognize what's the acid and what's the base. Looking at this, what's going to be acting like the acid? H2SO3 is the acid. Now there's two ways that you can figure that out. The first way is just looking at it like Jamie did. She saw that there's a couple things that kind of told her, I think. One is you have H2. This is fully protonated. You can't get it any more acidic. Another hint is, dang, this guy's got a negative, right? So it's going to be really hard pulling an H plus away from a negative. If anything, a negative wants to grab a plus. So it really looking like a base. The other thing you could do, which is much more complicated though, is look at the table. Both of these have H's. So they both have acidic properties. But one of them is a stronger acid than the other one. this one is a much stronger acid. He's listed in the table much higher. So he is going to act like an acid. He's going to force this dude to act like a base because he's stronger. But just like you said, is easier. You can see that it's the acid because it has H2. So this will be our acting like an acid. This will be acting like a base. Good. What would be our products then, Jarixa? What would be our products? Now remember, they have to be conjugates of each other.
I would take the acid first.
Okay.
And then I would take
so he's going to get turned into what?
base.
The base, which will be?
SO3 or H2 plus SO3.
How many H's do you have to remove?
Oh, one.
Just one. So it'll be HSO3.
Oh, okay.
Does it have a charge?
Yes, one.
-1.
Yeah, -1.
And if you're not sure, you know what you can do? I mean, it's going to take longer. Just look at the chart, right? The conjugates are all written there. H2SO3's conjugate is written there. HSO3 minus. We need the conjugate of, Victor, HS minus. But remember, HS minus is acting like a base. So you have to write its conjugate acid over here. What would you write? Just add an H plus to it. Add an H plus to this, you'd have H2S. And the plus and the minus, all right, they go to 0. Okay, so where are my two acids I'm supposed to be comparing here? James, where are my two acids I'm supposed to be comparing the strengths of? H2SO3 and H2S, right? Because this was the base, so that means he must be a conjugate acid. The other way you could tell is you can just look at them. H2S is fully protonated. Okay, look at the table. Which one of these is stronger? Sorry, which one of those is weaker? That's what you want to point the arrow towards. Which one is weaker? H2S? Everybody agree? Okay, H2S is a weaker acid, so we better point it. Get rid of this one. Okay. Always points towards a weaker acid. Okay, you do B. Try B. And then we'll talk about one more thing, and then we'll go to the boards. See if you can figure out which one's acting like the acid. Right? Like Daisy, which one of these is going to be acting like the acid? The HCN. Good. So this is your starting point. This guy is your acid. Write its conjugate base. Oh, it doesn't matter. A plus this plus that plus that. The order doesn't matter. Roland, we got to compare H2S and HCN. Which one's weaker? The HCN? Okay, so that's where we point our arrow then. Okay. I don't know. I just, some people agreed. HCN is stronger. Here's HCN. Where's H2S? H2S is right here. So which one's weaker? HCN. So you point towards the HCN. Is that what we did? Yeah. Point towards the HCN. Trust the Roland. Okay. So one more thing before we go to the boards. we want to be able to look at a chemical structure, a chemical formula, and just predict whether he's going to be a stronger acid than others just by looking at the chemical formula, make some predictions. So I'm just calling X any element on the periodic table, right, besides H plus, I guess. Okay, so I have some element. Now these elements are all in the same group in the periodic table. What's the group again, Daisy? Is that these, or is that the horizontal stuff? What's a group? Yeah, group is the vertical. Okay, so you're in the same vertical column. The larger the element is, Jonathan, then the blank, the bond it'll have with H. Right? So you've got to make it bigger. The bond is going to be spread out pretty much over a larger area. So overall, it's going to make it weaker. Okay, so now if this bond is weaker, right, that would result in a what acid, Jamie? Stronger acid, right? It's going to fall off easier. So that's going to be a stronger acid. Does that make sense? That's the logic behind it. Weaker bond, stronger acid. Now you have elements that are in the same period in the periodic table. Okay, going across. The more polar the bond, then the Teresa, this is a hard one. Now before you answer it though, there is logic to it. I know, I think I was picking on Daisy. And I said, Daisy, look at the periodic table, and there's half of your strong acids are there. Which halogen did she not name as a strong acid? F. Now what's so special about F? It's what? It's numero uno in something. It's the most electronegative element on the planet. So if you want to make a polar bond, it would be with F. But F is not a strong acid. So what would you say for this answer then? The more polar the bond, the weaker, right? Otherwise, HF would have been right up there. Okay. Last one, the more oxygens. Now, Victor, before you answer this question, the more oxygens present, the what the acid? Take a look at that list of strong acids. Where did they go?
You missed something. Right there.
Huh?
Right there.
No strong acids.
Oh, you keep going.
Here they are. Okay, here's our strong acids. The more oxygens you have, the better off you are, the better, yeah. Look at all those oxygens, H2SO4, NO3, O4. So yeah, the more oxygens you have, the stronger that acid will be.
I was like, what oxygens? But I saw them.
Okay, so that's it. So let's go to the boards, and we'll knock this stuff out, and then you guys can be on your merry way.
Okay, let's make sure we leave here at 12:05. I mean,
Oh, I have a
2:05.
whole extra set of problems for you.
Sorry.
Okay, so on this first one, number 47, what we're going to do here is decide whether the species on the left or those on the right are favored by the reaction. So you're just drawing the arrow. So you have to identify in there the two acids and draw the arrow of the reaction towards the which acid? Towards the weaker one. Yep. So identify in there the two acids. There's one on each side. And then compare them. You have the table, so you can compare.
Oh, it's already done.
Yeah, they're already written, so you just have to figure out what's acting like an acid. And don't forget all the stuff that you've learned so far. Like when you see hydroxide, that is a base, right? That's our whole definition of base. You see hydroxide, so I would definitely write base under hydroxide.
Oh, whoops. You know what I meant.
because he has to be the base, so he has to be an acid. So if he's an acid, his conjugate has to be a base. That means this has to be a acid. So what two are you comparing then?
It'll be this way because H2 would be at the bottom of the acid.
Yeah.
Oh, weaker. Okay.
There you go. Draw the arrow towards the weakest acid. So in the first one, hopefully you're pointing your arrow towards the weakest acid, which is water, right? Because you're comparing H2O and H3O3.
How would you say that?
So H2O is weaker. You see that, Daisy?
You just look at the table.
Yeah, just look at the table. And the water's at the bottom. You can't get any weaker than water. So then try the next one.
Because then they add more water. Isn't it you add more water, it's weaker? In a sense.
This has nothing to do with dilution and concentrations. We are just looking at identifying the dominant side of the reaction. And it always points towards the weaker acid. So you have to look at the reaction and find the two acids on both sides. So find the two acids on both sides.
How would you say aluminum hydroxide?
This is aluminum hexa water, right? Yeah, it's true. Hexahydrate. No, they call them hydrates. Aluminum hexahydrate. Hexawater. Aluminum hexahydrate. So if hydroxide is the base, that means this has to be an acid.
Yep.
So if this is an acid, this guy has to be a base on this side. Acid. Always point towards the weakest acid.
Oh, whoops. Sorry.
Okay. So they're both pointing towards products. Do the same thing to 48. See if we can all agree with 48. Try to identify the two acids. So which one's weaker?
This one. This one where is it? I lost it. H.
Oh, yeah, there's H2CO3. Oh, they're right on top of one another. H2S is barely weaker than H2CO3, right?
I thought it was H3.
No, H2.
Yeah.
Yeah, so H2S is just barely weaker.
2S?
Right? H2S.
Is
It's-
right. Yeah.
It's
Oh,
more
yeah.
on the bottom of the table than the other guy is.
So we're going to have this table on the test?
Oh, yeah. Just know how to use it. So the acids you compared on this one hopefully were these two, right? And which one's weaker? H2S. Which two acids did you compare on C? H2O
And HCN.
and HCN are acting like the acids. Which one's weaker?
Yeah, H2O.
H2O.
Got it.
about the last? How about D? Towards reactants again? Comparing HCO3 minus and HCN. Yep. We're all going towards reactants. Okay. So last one. What you're asked to do is just to, by looking at these guys, figure out what the stronger acid is, and then give a reason. That works. You can say fully protonated. I bet they're both in the table, too. But yeah, more H plus. Now B, I don't think you can use the table for B.
Did you say that's on the strong acid list? Oh, no, it's not.
Mm-mm.
Oh, it is.
Mm-mm.
It isn't. No.
That's H2SO4. So think about the only other options that you were well, go on to D. Save B for last. Yep. Because it's what?
Do you go by electronegativity? Or no?
Oh, okay, yeah.
Now Jonathan was onto something here. Look at sulfur and selenium, right? Which one is you can go two different routes there. You can go with electronegativity, or you could do the size thing, right? If you do the size thing, which one is bigger? SE is bigger, right? Because it's closer to the francium. So if SE is bigger, that means it's stronger, right? Because that'd be a weaker bond. Try the other way. Try the polarity thing. Which one is more polar, sulfur or selenium? Sulfur is, right. I mean, diagonal from F. So that means that would have to be weaker. So both scenarios, the selenium acid comes out stronger. And then in D, which one did you pick? Why? Good, more oxygens. All right, so that's it. So have a good day.